Your question from the book?
It's page 68.
What worksheet? 2 point up at the top.
It's just the.
No, it'll say up at the top right. It'll say 2 point something something over the right.
2.28 rate diagram.
Okay, 2.2H rate diagrams. All right. And what page was it again?
68.
68, yes.
And then the volume one, because I don't get volume graph.
Okay. So this is 68. In your book. I'm going to take this off because otherwise it's smacking up against the counter. There we go. And if we decrease the volume, all the concentrations are going to increase. And if all the concentrations are increasing, there's going to be more collisions. Yeah? And if there's more collisions, that means that both rates speed up. Which rate speeds up more? Whichever side has more gas molecules speeds up more. And I'm noticing, just in case everyone's wondering, that Kate is on his phone again. And now that's recorded for posterity and is going to go on my YouTube channel. Yes! Okay. So both rates speed up, but because we have more gas molecules over here, the rate is affected more. By a change in volume / pressure. Okay, so both rates speed up, but the one with more particles speeds up more. Yes? Not for rate, no. For rate, for the rate. Okay, so what we're talking about right now is we're saying what, not in terms of the shift, but in terms of what happens to the rate. The forward rate, which has more gas, the reactants have more gas molecules. The reverse rate has fewer gas molecules, and so the forward rate, in this case it's dashed, I don't know what possessed me to make the forward rate the dashed one, it goes up more than the reverse rate.
But how does is forward the forward stuff? Shouldn't the reverse be more?
Well, if the reverse rate is faster, then we would be shifting towards the reactants. Are we shifting towards the reactants? If I squish the container, and I got 2A, I think what's happening is you're confusing rate with shift. Yeah? So if we squish the container, the direction is going to shift this way. But it shifts that way because the forward rate speeds up more than the reverse rate does.
Why does the forward rate spike up?
Because it has more gas molecules. Because you're affecting two concentrations.
Oh.
Yeah? Because it's a squared term rather than just a single term. Yeah? Okay. So our forward rate speeds up more, and then what will happen is that the two rates will then end up meeting in the middle. Anything else before we go on to some multiple choice? Yes. Page 81. Number 11? 9 through 11, okay. So what we've got is, this is page 81. Which of the following combinations describes the effect of increasing the pressure of the system? So if we're increasing the pressure, that means we're decreasing the volume. So let's remember that's like this. And over on our left-hand side, we have 2 gas molecules. And on our right-hand side, we have 4 gas molecules. And so if we squish it, our reaction rate, everything becomes more concentrated. So just like in the last question, the concentration increases, all the concentrations increase, therefore all the rates increase because there's more collisions. So far so good? Yeah, okay. So we're looking at our reaction rate increasing. So it's one of those two. And then we have to say, which way does this make it shift? If we are increasing the pressure, we are going to shift to the side with fewer gas molecules. And the side with fewer gas molecules is over here. And yield, do you guys remember what yield is? Yield is the amount of product. Okay, so yield is the amount of product. So if we have shifted to the side with fewer gas molecules, are we getting more product or less product? Less product. Yeah, because we've shifted towards the reactants. So that means our equilibrium yield, our equilibrium amount of H2 decreases. Yeah? Okay, which of the following combinations describes the effect of increasing temperature on the system? We have delta H is greater than 0, which means that it is positive. So that means I don't even need to write the whole reaction. I can just be like, okay, I got this thing and I've got my heat term over here, my kilojoules are over here. And if we then increase the temperature, what happens to rate? Everybody. It increases. If we increase temperature, rate increases. So it's either going to be B or D. And then if we increase the temperature, which direction do we shift? To the right, to absorb the extra heat. Okay, and so we are going to get more product. Remember, yield is amount of product. And in this case, specifically H2. And since we're shifting to the right, we're going to get more product, so it's going to be D. What is the result of a small increase in temperature? does the forward rate get faster or slower if we increase temperature? Faster, because the particles are moving more quickly, they're going to collide with more energy, and they're going to collide more frequently. So, and if you know how to play the multiple choice game, you'd be like, oh, forward rate is higher, because 3 of them have the higher option, so that's probably the correct one. And reverse rate, once again, I've got 3 of them are higher, so I would probably guess that. But also, if you increase temperature, what happens to rate? It gets higher. It doesn't matter whether it's the forward or the reverse. Both forward and reverse are going to get faster. And so now we are down to these 2 here. So we have to decide, is our equilibrium constant going to get higher or lower? We already decided that if we increased temperature, then we're going to shift to the right, which is going to give us more product. And less reactant. And so KEQ is going to get bigger. Yeah. Anything else before I go to some multiple choice? Yes. 18 on page 83. Page 83, number 18, yes. Which of the following combinations describes the effect of removing a catalyst from the system? And I assume the system is up here. Here's our system. If we remove a catalyst, what happens to our rate? Is the rate going to stay the same, or is it going to decrease? Those are our 2 choices. You guys are killing me. You're going to make me say it? With this voice? You can't say it? No, what? If I remove a catalyst, what happens to the rate? It decreases. Catalysts make rate faster. If you take them away, it decreases. What happens to our yield? Remember, that's the amount of product.
No.
Do catalysts cause a shift? Catalysts do not cause a shift. And if they don't cause a shift, then there's going to be no change in the amount of product. So we're looking at that, which gives us the overlap on B. Anything else? Yes. Number 9 on page 75. Number 9 on page 75. Okay. So this is a crazy little thing here. So what we see is that we're going to interpret this diagram here. This is page 75. We are at equilibrium, and then we had a stress that caused no spikes. What was the stress if there were no spikes? That was temperature. And because we have a positive heat term, so that's going to be on this side, and we shifted towards, we got more product, so we shifted to the right. And if we shifted to the right, did we increase temperature or decrease temperature? We increased temperature, okay? So that's our first one. So at 4 minutes, we increase the temperature. At 10 minutes, that's our next stress. What was our stress at 10 minutes? Okay, so at 10 minutes, our stress was a decrease in the concentration of CO. And then the system shifted to the right. Oh, Jesus, sorry. And then our next change was at 14 minutes. And at 14 minutes, all 3 concentrations went down. What could cause all 3 concentrations to go down? Pressure, volume. And if they're going down, if concentration goes down, did we make our space bigger or did we make our space smaller? We made the space bigger, so all the concentrations went down. So at 14 minutes, we increased the volume, decreased pressure. Is good? Cool. Yes. 75A? Okay. This is page 70. And we're looking at question number 5. So we've had an increase in temperature. That's going to cause a shift to the left. So that means that H2 and I2 should go up and HI should go down. So H2 is going to go up and it's got a coefficient of 1, so that's going to be X. I2 is also going to go up because it is being made. And it's also got a coefficient of 1. HI is being used up. And it has a coefficient of 2, so it's going to go down by 2x. Yeah? Cool. Anything else? Yes? 76, number 12. Okay. Whew. By the way, there's no questions like this on your test, just in case you're worried. But worthwhile looking at, yes?
What does that look like?
All you need to do is you need to say, oh, look, what happened at T1? At T1, I had a stress. What was my stress? My concentration of N2 went up. No, but like let's take a look at it anyway, right? So my concentration of N2 went up.
And H2 were decreased.
No, they weren't. The system did that.
Yeah, this is it.
The system did that, and then we shifted right. At time 2, the stress was, oh, look, we have a spike, but not just one spike. There's 1 spike, 2 spike, 3 spikes. When everything spikes, what does that tell you? That is a change in pressure, volume. And if they all went up, all the concentrations increased, did we make the volume bigger or smaller? Did we make the volume bigger, or did we make the volume smaller if all our concentrations got bigger? We made the volume smaller. Yeah? So we decreased the volume, which means we increased the pressure. And that resulted in a shift to the left. Then at time 3, there's no stresses showing on there. And if there's no spikes on any of those, what must the stress have been? It must have been a temperature change. And in this case, we made H2. And if we're making H2, that means we're shifting left. And if we're shifting left and my heat term is here, what did we have to have done to the temperature? Do I want my arrow to look like this? Or do I want my arrow to look like this? Up, okay? So my temperature increased and we shifted to the left. Is good? Okay. So these aren't as crazy as they look. You just look and say, like, what happened right at that time? And then it's just a shift after that. Anything else? Okay, while we find things, if there is anything else to find, we're going to do the equilibrium review, number 55. 55. Which of the following statement describes the effect that a decrease in volume would have on the position of the equilibrium and on the concentration of H2? Well, when we're dealing with position of the equilibrium and volume change, we have to look at the number of gas molecules. On the left-hand side, we have 1 gas molecule. On the right-hand side, we have 1 gas molecule. Okay, and 1 gas molecule, 1 gas molecule. That means, will there be a shift? No shift. So we're either dealing with A or we're dealing with B. If we decrease the volume, what happened to the concentration of H2?
Oh, I thought it's constant, but
It increases, yeah, because of the volume change.
No, I thought
Not because of any shift, though.
Oh,
Yeah, it increases due to the volume change. Is good?
Yeah.
Cool, cool. All right, 72. Oh, we did 72. That's okay, we'll do it again. The temperature of a given system, this is 72, is increased while volume is kept constant. A new state of equilibrium is established in which there is an increase in, so we need to figure out which way it shifts. We have a positive delta H, so that's going to be 41 kilojoules over here. We increase the temperature, so that's going to cause a shift to the right. And that means that who's going to get increased? Is it CO or CO2? CO is going to get increased. So we have either A or C, or sorry, A or B. And do we have an increase in KEQ or a decrease? Well, we have shifted from reactants to products. So the concentration of products goes up, concentration of reactants goes down. So we have a bigger number up here and a smaller number down here. So KEQ is going to get bigger. So that's going to be an increase in the KEQ.
So that reactants usually decrease, right? That's what we have like endothermic reaction and the
What?
increase in temperature.
Oh, yeah, if there's an increase in temperature, we shift away from that, the heat term. Yeah.
Okay.
Yeah.
And so like on the side of the heat term, like concentrations decrease.
Yes.
And then on the other side, concentrations increase all the time.
Yes. If you've increased the temperature.
Okay.
Yes. Yes. Yes, yes. Okay, and number 95. Oh, I hate these ones because this is except. So we have to find the one that's not true. Okay.
You know what? I found what is not true, but I don't understand why everything else is true.
Okay, well, let's find out. Okay. Adding H2 to the equilibrium mixture will have all of the following effects except, well, if we go there, it's going to shift to the right, which is going to use up CO2, so it will reduce the amount of CO2. So that is correct. Does it increase the amount of CO? Well, we're making it, so yes, it increases the amount of CO, so that's correct. Does it change the value of K? Well, we haven't changed the temperature, so no. So this is false. Only temperature changes K. Does it increase the amount of H2O? Well, we're making H2O, so yep, it increases the amount of H2O.
Hold on, how can it increase the amount of H2O if like we have like more H2O, so therefore the H2O should decrease so that we have
No. We increase the concentration of H2. We do that. And then we shift away from the H2.
Yeah.
And we shift towards H2O.
So that like the original concentration of H2O was not present, or
The original concentration was what?
of H2O. Was it like present at that time?
Yes, because we are at an equilibrium mixture. So we are at equilibrium, so we have some of each.
Okay.
Yeah?
So that like if we increase the concentration of solid, right, it is gonna increase develop something which has that, right? Okay.
Yep.
And
Yeah?
yeah.
Cool. And then it shifts the equilibrium forward. Well, yes, we just said that, so that is also correct. So our answer, except, is this one. And that's it for questions that people have given me so far. Is there anything else people have on their minds? Yeah. Yep. 100 and what, sorry? 18? Number 4. Okay. Okay, so here we go. We want to know if the reaction will go to completion, reach a state of equilibrium, or not occur at all. So what we're looking for is we're looking for where our maximum entropy and minimum enthalpy are. Minimum enthalpy is always with the heat term. So we can actually go through here and we can be like, ooh, minimum enthalpy. And we can say, oh, that's a negative value. That means my kilojoules are over here. And if my kilojoules are over here, that means this side has the minimum enthalpy. Here we have positive delta H, so this side has minimum enthalpy. Positive delta H, so this side has minimum enthalpy. There's our heat term in the products. So products have minimum enthalpy. We got our heat term over here. So our products have minimum enthalpy. Another negative delta H, so that means kilojoules are in the products. So there's another minimum enthalpy. And finally, we have a positive delta H, which means our kilojoules are in the reactant. So that is our minimum enthalpy. So enthalpy is pretty easy to deal with. Just look for your heat term, and that's the direction that the reaction is being pushed, by enthalpy. Now we need to go through and say, what is entropy doing? Okay, and so we can look and we can say, which is more random, gas or aqueous? Gas is more random, and we're looking for more random. And so that's going to be maximum entropy. What that means is that minimum enthalpy is saying go to the right. Maximum entropy is saying go to the left. And when you have one that says go to the right, and you have one that says go to the left, that's going to be an equilibrium. Yeah? Now, in terms of spontaneous and non-spontaneous, spontaneous, you only need one arrow pointing to the products. So you could have an equilibrium or you could have completion. And it will be spontaneous. Non-spontaneous means no go. And there should be like an X here, because that, I need to fix that. X. So this one, it has an arrow going forward, so that is spontaneous. In our next one, we've got solid and liquid versus aqueous gas. And so this side over here is more random. So that's going to be our maximum entropy. So that means that maximum entropy is pointing towards the products, minimum enthalpy is pointing towards the products. That means we're going to have a one-way arrow. It goes to completion. And because it's got at least one arrow pointing forwards, that is spontaneous. In our next one, we've got two gas molecules on the left and only one gas molecule on the right, which means that this side is more random because it's got more gas molecules. So there is our maximum entropy. So both maximum entropy and minimum enthalpy are pointing that away. So this is going to be no-go. And it's going to be non-spontaneous. Do we want to do any more of these? We're good? Perfect. Yes. No. Yeah. So this is 7 on page 119. So we have an exothermic reaction. So we have A in equilibrium with B, and there's our kilojoules. Okay. And we are reaching an equilibrium. And if we're reaching an equilibrium, that means that maximum entropy and minimum enthalpy must favor opposite sides. Since it is exothermic, B, the products, have lower enthalpy. And therefore, minimum enthalpy favors the products. And if minimum enthalpy favors the products, and we have reached an equilibrium, what must maximum entropy do? It must do the opposite. Maximum entropy must favor reactants, the opposite side, to reach equilibrium. So for our reactants, we have high entropy And we have low entropy. Therefore, entropy decreases as the reaction proceeds. And since the reaction is exothermic, enthalpy decreases as the reaction proceeds. Cool. Anything else? Yes. 104 and 105 on the review, yes. Okay, so we have this equilibrium, and we are in a 2-liter vessel, and we have 3 moles of H2, so 3 divided by 2 is 1.5 molar. 4 divided by 2 is 2 molar Br2. Oh, and this one was H2, so that's H2 there. You would show that calculation if you were doing this in a written response, but as multiple choice, so you can just be like, oh, just divide by 2. There we go. And those are initial, right? Because those go in and then they are allowed to reach equilibrium. So these are initial, which tells us what kind of a situation is this? This is a race table situation. At equilibrium, HBr is 2 molar. That's at equilibrium. Calculate the value of K. All right, so we have RICE. We know this is 1.5. We know this is 2. This is 0. And we know that this is 2. So to go from 0 to 2, we had to go up by 2, which means that we need to go down by 1 on each of these because we have a coefficient of 1, a coefficient of 1, and a coefficient of 2. All right, so we have now 2 minus 1 is 1, 1.5 minus 1 is 0.5. And now our KEQ is going to be HBr squared over H2 times Br2. And obviously, because this is a multiple choice question, you can just be like, oh, I'm going to square 2 and put it over 0.5 times 1. Okay, so that's going to be 2 squared over 0.5, which is 4 divided by 0.5, which is 8. Yeah? Okay. If the reaction is repeated at the same temperature, but using initial concentrations of 1, 2, and 4 molar for the H2, Br2, and HBr, in which direction will the reaction proceed? What is this asking us to use? What tool? It's asking us to use Q. And we know our KEQ because we just solved for it. Yeah, so our KEQ is 8. And our Q is going to be HBr squared, so that's 4 squared, over H2, and the H2 is, or the Br2 is 2, and the H is 1, so that is 16 divided by 2, which is 8. And if KQ is equal to Q, then the answer is D. It's not going to shift either way. It is already at equilibrium. Very nice. Yes. 11 on the written, yes. Okay, so NaOH is added to this solution. So remember, anytime you have a solution and you add a solid, don't leave it as a solid. If it's got sodium, it's going to be soluble because all alkali ions are soluble. So we're really adding this into like a water-based solution, yeah? So it's going to dissolve. And we're going to get Na+, and we're going to get OH-. Now, do we care about both of those ions or just one of them? We just care about one of them. Which one do we care about? We care about the OH because Na doesn't react with anything because it's an alkali, it's soluble with everything. That means that Na+ is going to be a spectator ion. Now, who can hydroxide react with? It can react with H. Whoops, that was supposed to be a highlight. So we're going to have H plus OH minus is H2O, which means that hydrogen is getting used up in this reaction here, which means that is decreasing. And if H is decreasing, which way will the equilibrium shift? It will shift to the left. And if it shifts to the left, what color change would we observe? It would go from orange to yellow. So I didn't really write that in a very nice way. I would say, you know, my first point would be OH minus reacts with H plus. Therefore, the concentration of H plus decreases. Secondly, therefore, the system shifts left to make more H2, to make more H plus, sorry. And then 3, the color changes from orange to yellow because we've shifted left. Yes? How do I know it's a spectator ion? Na is always a spectator ion. Yeah, so if you've got your table, your data booklet, and we've got our solubilities. Alkali ions, this is on page 4. Alkali ions are always soluble, so they're not going to react with anything, okay? And the other one that you need to know is nitrate. Nitrate is always going to be a spectator ion also. Now, why am I not including hydrogen and ammonium and acetate in that? Because they can react in acid-base reactions. So they won't necessarily always be spectators if we've got acid-base stuff going on. But The alkalis and nitrate are always spectators, and so you can just ignore them in anything to do with an equilibrium. Excellent question. Yes. 20. Written response number 20. In an experiment, a student places the above equilibrium system into a cold water bath and notice that the color of the red, the intensity of the red color increases. So when we put it into a cold water bath, that tells us that temperature has decreased. And if the intensity of the red color increases, that tells us that in a cold, I keep forgetting these are written response, so you actually have to explain yourself. In a cold water bath, red color became more intense, therefore the system shifted right. And so if we are shifting to the right, and there's a temperature decrease, then the heat term must be on the if we shift right upon temperature decrease, heat term must be on the right. That means that the forward reaction is exothermic. So the student said that the equilibrium was exothermic, and when we say that, we mean the forward one. Okay, so yes, I agree with the student. I'm sad there's no video component with this right this moment. That's okay. Yes. 23. Okay, describe how the following changes will affect the given reaction. Describe any shift or lack thereof in terms of Le Chatelier's principle. Describe any shift or lack thereof in terms of collision theory and rates. Well, this is going to be a pain in the ass. Good Lord, what have you done to me? Okay, so what we have is if we add H2, okay, if we add H2, the system shifts to the left. And then in terms of Le Chatelier, to use up the extra H2, to use up H2 and bring concentration of H2 back down. In terms of rates, the extra H2 causes more collisions in the products. Therefore, the reverse rate increases. Forward rate is unchanged. Since there's no change in concentration of reactants. Therefore, my reverse rate got bigger. My forward rate remained unchanged. Therefore, we are shifting left.
Miss Beth,
Yes.
is because the concentration of CO2 gonna decrease in this case, and CO and H2O gonna increase?
H2 and CO2 are going to decrease. CO and H2O are going to increase. Yeah. Do we want to go through all of these, or is there a specific one you would like to do? You're good? Okay. Would you like to go through any? Like, because we could do like one more maybe. We could do a temperature or a volume or. We're good.
Will be no change. Would be
Catalyst is no change.
yeah.
Yeah. Because it speeds up both rates equally.
Yeah.
We're good? Yeah.
Actually, you know what? If we decrease the temperature here,
Yeah.
the concentration of CO2 and H2 is gonna increase, and the concentration of CO and H2O is gonna decrease.
Yes.
Now logic makes sense.
Yes. Yes. Yep. Yep. It's a solid, so it will have no effect on the position of the equilibrium. There will be no shift. Anything else? Yes. Test format. 24 multiple choice plus 16 marks in the written response. So it's going to be out of 40.
How many Lechat's principles do you have to write?
I don't know.
Oh, you don't know. You can't tell us? Oh.
What do you mean? Like I memorized every question?
No, I mean like how many? I mean like manually write down rate, describe in rates, and describe in Lechat.
I don't even know which version I'm giving you.
I don't. Oh.
So I got like 10 versions of this test.
Oh, you do?
Yeah. Yes. Unless there's 2 or more. And the chances of coming across that are like slim to none. So I wouldn't worry about them. Liquids just be like, liquids don't count. Yeah. Solids don't count, liquids don't count. Yeah. Thank you to my back row. You guys have done a stunning job asking lots of questions. That's fabulous. Anybody else got any questions? Or you guys, if you have any more? No? Okay. Shall we start our new unit then?
Wait, is this acid and base 1? There's a second version?
There's a second part, which is like applications of acids and bases. Oh. James, you chose to take chemistry 12? There's going to be chemistry in it. Oh my God. Alrighty. And we are going to start, I know this is going to sound weird, but we're going to start on page 66. What's that? Can we just take a break? Yeah, we can take a break for 5 minutes. 5 minute break? 5 minute break. Oh yeah, and class ends at thing today. Oh yeah. Oh my God. Sorry, I was thinking it was a day, like a non-flex day. Yeah, we're done. We can just be done. Good question. Tomorrow, I'm going to give you a handout that has your spring break homework on it.
Wait, spring break homework?
Yes.
No, are we in Chinatown? No.
You guys get to watch a 7-minute video and fill in the blanks. Oh my God, 7 minutes. Then you get to watch a 13-minute video. We've now spent 20 minutes. Okay?
Wait, the test is tomorrow, correct?
Yeah. Oh, there's 20 minutes, and then there's some Hebden questions to go along with that.
Like that?
But only 1, 2, 3, 4 questions. And then there's a 12-minute video, so now we're up to 32 minutes.
Is it always spring break?
Yes, this is spring break. Oh, not even any questions with that one. A 9-minute video, now we're up to 40 minutes.
I mean,
Oh, no questions.
Most of it's just watching videos.
Yeah, it is. It's mostly just watching videos. It's like an hour of videos and then a few little questions here and there. Okay? Fill in the sheet. I am going to check to see if it's done. When you come back after spring break, if it's not filled in, I'm going to give you a lab mark for it. And if it's not done, then you're going to do bad on the lab mark. Okay? Because we haven't done any labs yet. So you have a chance to get a 10 out of 10 on a lab mark. Yes? And all you have to do is fill it in and do the Hebden questions. Yeah? Yeah.